Like I said, today we're going to start in on the SN1 reaction, and we're going to learn the ways in which it differs from the SN2 reaction, and also maybe a few ways in which it's quite similar. But that's going to be our main topic today, is the SN1 reaction. And of course, SN1 stands for substitution nucleophilic unimolecular. And so we're going to find out that whereas the SN2 reaction involved two molecules in its rate determining step, in that case it was also very easy to tell which was the rate determining step because there was only one step, so it had to be rate determining. However, in the SN1 reaction, what we'll see is only one species, only one molecule is involved in its rate determining step. So in a typical SN1 reaction, we could take maybe, I don't know, church butyl bromide and react it with water. Generally, we heat these in protic solvents, and almost always, maybe not entirely always, but certainly almost always, I think you'll find in an SN1 process, the solvent and the nucleophile are the same thing. And in the end, we will get a substitution product. In this case, the oxygen and the alcohol comes from the water molecule. Now, of course, this equation isn't balanced. If we wanted to be picky about it and very careful in terms of writing a balanced equation, it would probably look like church butyl bromide plus 2 waters yields church butyl alcohol plus hydronium H3O plus bromide. That now is balanced both for mass and for charge. And I point this out because when we look at the energy diagram, that's where we're going to want to be very careful about making sure everything is balanced. Ordinarily, we organic chemists are pretty sloppy about balancing reactions for mass, but we can't afford to do that with energy diagrams. We need to make sure at each stage along the way we're balanced for both mass and charge. And I think you'll agree this equation is balanced for mass and and also balanced for charge, right? The total charge on both sides of the equation is 0. We have 2 waters here, one of which goes to form the hydronium ion, and the other which provides the oxygen of the OH group. So unless I've completely lost it, which is always an open possibility, this equation should be balanced. And so if you want to see what that would look like in terms of a balanced equation, I would say probably the best way is to balance it like that. So what we find is that although we can get a nucleophilic substitution with a tertiary substrate, it goes through a rather different process, and the mechanism's rather different from an SN2 process. Although we will find, like I said, this is going to be a unimolecular reaction, which again means there's only one molecule involved in the rate determining step, and the rate law is first order. So in this case, our rate law would look like this. Rate is rate constant. Again, for this particular example, it would be rate constant times the concentration of church butyl bromide. I'm going to use Tbu for a church butyl group. So that's what the rate law would look like for this particular reaction. Or in general, the general form of the rate law would be rate is rate constant times substrate concentration. So this is a first order rate law. The reaction exhibits first order kinetics. And I think if, even without knowing the mechanism, even just looking at our equation, all we're given is our substrate, and then the species which is to be both our solvent and our nucleophile. Well, kinetically, it would make sense that if this is the solvent, then solvents fall out of the rate law anyway, just because they're in such large quantities compared to everything else, right? Our church butyl bromide is essentially swimming around in a big ocean of water. And it's very common, again, for an SN1 reaction that the solvent will be protic and the solvent will double as the nucleophile. And we'll get to why that is later. But even if the water is involved in the reaction at some point, which it of course will be, obviously, where else would we get the oxygen from? But even with that being the case, since the water is in such a large excess, by definition, that's what it means for something to be a solvent, no wonder it doesn't show up in the rate law. anything that is in an extremely large excess, even if it's involved in the reaction, well, as a result of being in such a large excess, it means that its concentration term has an exponent of 0, right? And anything to the 0 power is 1. So anything in a large excess effectively falls out of the rate law. It doesn't show up. So no wonder it's a first order rate law. Right, so that's the general rate law for an SN1 reaction, first order rather than second order. So again, I don't know, it's so long ago, it's like 30 years ago, but I remember distinctly finding that confusing in college, that the SN1 reaction is 2 steps and the SN2 reaction is 1 step. So remember, the number in the name tells you the molecularity of the reaction or the order of the reaction. It doesn't talk about the number of steps. Good, so I think I've done enough of a buildup here. What then is the mechanism? Well, we'll look at a couple of examples of SN1 reactions. The first step of the mechanism involves the leaving group just leaving, unassisted by anything else. So as a result, we will get a carbocation. That's what you get when you take away an electron pair from a carbon. And already we can see, no wonder tertiary substrates work so well work so well in SN2 and SN1 reactions. If we're going to get a carbocation, we want that carbocation to be as stable as we can get. So no wonder. So this is going to be our first intermediate. Yes, we also do get a bromide ion, and you'll see we'll get that in the end as well. But certainly the major organic species at this point is this carbocation. And this, by the way, is the rate determining step. You can write RDS for rate determining step, or another perfectly good thing to write for the rate determining step is slow. That's the slow step. And I don't think that's surprising at all. You kind of would expect that if a step requires the leaving group just to leave, I don't think anyone would really expect that to be a kinetically fast step, because we have a considerable energy barrier to get over to lose the leaving group like that. So remember, again, this carbocation, remember carbocations are planar, right? That's an sp2 hybridized carbon. So that's the first step. The second step involves our nucleophile attacking the carbocation. Like I said, most commonly, the nucleophile and the solvent are going to be one and the same. So that's going to give us our product protonated, right? The conjugate acid of the product. Couple things here. First of all, this step is fast in comparison to that one. So that's why the solvent doesn't enter the rate law. That step is very fast kinetically, certainly compared to this one. Another issue I want to deal with right here is a lot of you are probably wondering why I have to use a water molecule. Why can't I use OH minus? Because then I'll go directly to the product. And it's an understandable question. But the reason we can't use OH minus is because it's not there. Always remember to look back at what you're given when you're looking at any reaction, mechanism, or otherwise. And all I'm given is my substrate and water. I don't see OH minus or NaOH or anything like that mentioned. And yes, water does auto-dissociate, right? 2 waters goes to OH minus and H3O plus. And there's a water product constant where we learn that at neutral pH, OH minus concentration and H3O plus concentration are the same at 10 to the minus 7th molar. Well, that's going to be at least 7 or 8 or 9 even orders of magnitude, too small to make a difference. It wouldn't make any sense to use a species in a mechanism when its concentration is so negligibly small compared to everything else. So that's how you know that you can't use OH minus here. And that's, again, a good reminder, when you're drawing mechanisms, you need to look repeatedly back at what you're given and make sure that the species that you draw in your mechanisms, that those species make sense based on what you're given. So that's how I knew to put a water molecule here and not OH minus. Make sense? So we're nearly done, not quite done, but we're nearly done. I would say at this point that the SN1 reaction is officially over. And this leads to something that I think is a little confusing, that your book presents that's pretty similar to pretty much every other textbook I've worked with. It's something I'm really not a big fan of. And we'll get to that when we discuss the energy diagram. I hope to make that a little clearer than what you find in your book. But at this point, the SN1 reaction is done. We're done with the nucleophilic substitution. The way you know that is because we've replaced the leaving group with something else. We've replaced the leaving group with something else, and that fulfills the definition of a nucleophilic substitution reaction. So the SN1 technically is over at this point. We're not done, though. We need to get to a neutral product. And so in order to do that, we need to pull off a proton from that oxygen. And so that means we need to find a reasonable base. How do I know what to use? How do I know what to put down for the base? Well, I need to go back and look at what I'm given. All I have is, besides my rapidly dwindling supply of substrate, all I have is water. So again, I can't bring in an OH minus ion or something like that and just craft that out of thin air. No, we need to use what we're given, and therefore we'll use a water molecule. That's the only thing I can see that we're given that can act as a base. And you wonder, well, maybe we can use a bromide ion. And I understand the sentiment, but there's two good reasons at least why it doesn't make sense to use a bromide ion here. First of all, because bromide ion is a terrible base, and I think you guys know that by now. It's the conjugate base of HBr, which is a really strong acid. And someone in chat is bringing up the other reason. So besides bromide being a terrible base, which I'll just say, I think I can think of maybe one example we'll get to next term where we wind up using a halide ion as a base. And the reason is, in that case, you'll be able to verify it when you look at what we're given. There literally is nothing else present that can act as a base. So we have no choice in that case. We have to use the halide ion. Here we do have the water, and not only that, since we know that water is the solvent, again, what does it mean when something's the solvent? It means there's a lot of it, that molecules of water far outnumber by maybe 10 or 15 or even 20 orders of magnitude all of the other species. So it doesn't make sense to use Br minus as our base when it's outnumbered so much by water molecules. So that's why we're going to use water as our base, and we know how to draw that mechanism. We use water to pull off the proton. We break this hydrogen-oxygen bond. Those electrons go on the oxygen and neutralize the plus charge, and we're left with our neutral product, tert-butanol. And so that's also, I guess, where our H3O plus ion comes from. But the major organic product, in this case, will be the alcohol. So this is a typical SN1 reaction. Water is not always the solvent. But again, any other protic solvent, I think you'll find, not 100% of the time, pretty darn close, that a protic solvent is involved, and that protic solvent doubles as the nucleophile. So what else besides water are things that we know are protic solvents? What about alcohols? Carboxylic acids are protic, and I would say primary and secondary amines are protic. So any of those would be a good choice as a solvent for an SN1 reaction. Good, so I think that's enough about that. Oh, I should also say, of course, this last step is definitely fast, very fast for sure. Kinetically, proton transfer steps are the fastest that there are. So there's no way that that speed is going to be anywhere near as slow as that first step. So again, I would say, yeah, tert-butanol or tert-butyl alcohol. Yep. So where was I? Right, so again, at this point, the actual SN1 reaction is technically done at this point, but we do have one more step. And I don't know about always, but that's very common with SN1 reactions, that you will have an extra step just to get you to a neutral product. Remember, you always want to get to a neutral product at the end. I can't think of an exception anyways. Good. Any questions then before we get to the energy diagram, which is where I'm going to differ from the book a little bit? Yes. Well, I think if you used K, the question is, could you use OH minus in the mechanism if that were in there? I think if you put too much KOH in here, you'd start getting E1 reactions, or maybe even E2, because that's now a strong base. So you need to avoid strongly basic species to be able to get a reaction like this. And we're going to go over that next time, how you know which is going to happen. But I think you'll find that it's pretty, you don't have to do a whole lot in terms of making everything weird before you get a pretty bad mixture. But I've got the flow chart. We'll go over that next time. We need to use something as a base to get rid of that proton. And unfortunately, the most basic species we have around in any quantity is water. So that's how we know to use that. Good. Other questions then? But no, it's a good point, and for me, this I feel was something worth repeating. When you write a mechanism, you need to make sure that the species you invoke makes sense based on what you're given. That's an extremely important idea that we'll take all the way through next term as well. What causes the initial bromide to break off? Well, just because the bond is polarized, right? Bromine is more electronegative than carbon, and so, but that's the only thing. Other than that, there's no assistance really by anything else. And so no wonder that's the slow step. Now, I don't think bromide is going to be breaking off so much in a bottle of tert-butyl bromide. Maybe a little. I mean, anything will decompose given time. I think a combination of that and the fact that we're in now such a polar environment with the water, maybe that will help to polarize the bond further, but the water molecules kinetically are not involved in that first step. And you can tell that because there's no arrows involving water molecules in that first step. But I would say a combination of the polarity of the bond and the polarity of the reaction mixture. But yeah, the driving force is not terribly strong. That's why that step is the slow step. And the others are in comparison much faster. So I hope that helps, but that's the best answer I think I can give. Good, other questions then? All right, well, let's draw our energy diagram. And again, here I believe I'm going to differ in some significant ways from what your book has, though I will let you know what your book has. And I mean, I don't think they're entirely crazy. I see why they're doing what they're doing. But I just think I have a better way and a clearer way of explaining it and drawing it out here. So energy in some sense on the vertical axis, right? Reaction coordinate on the horizontal axis. Certainly at the beginning, and here again, I'm going to refer to the balanced equation here. But somewhere on here, we're going to have our starting materials. This will be our tert-butyl bromide plus 2 water molecules. And we'll, again, be careful that everything's balanced all the time. After the first step, we're going to go up to our carbocation intermediate. And we still have the 2 water molecules. And we also, in addition, have a bromide ion. So somewhere up there is going to be the carbocation intermediate. Of course, there will be a transition state between them. I'm going to call that TS1 because we'll have multiple transition states. And so that's what the first step looks like. And again, it makes sense that's going to be the slow step. Look at that energy barrier we've got to get over. We then have, again, this other intermediate, this, where'd it go? This oxonium ion, as we call it. O-X-O-N-I-U-M, oxonium ion. That's a term that means something with an oxygen with a plus charge. And so I think that will be a little bit lower. I don't know that I can promise you always, but it kind of makes sense to me that that will be a little bit lower in energy. Simply because in the oxonium ion, everything obeys the octet rule, and carbocations don't obey the octet rule. So that would be my rationale. I don't know that I would be confident that that's always the case, but I think it should in general be. We still have a water molecule and we still have a bromide ion. And again, there's going to be another transition state between those two. You always have to go over some kind of barrier. Might be somewhere around here. And then at the end, you're going to get your products. For us, this will be the tert-butyl alcohol, H3O plus ion, and bromide ion. So again, there's going to be some transition state somewhere. There's always a barrier to get over. Something like this. I certainly would be negotiable on the relative heights of the three transition states. That's going to vary from based on the particulars of the reaction. But I think you'll find that in general, an SN1 reaction is going to have an energy diagram something like this. Now, what does your book do? And again, what pretty much every other book I've ever seen does, including the one for Chem 222, by the way. What they do is they kind of telescope together these two steps so that effectively we're going straight from the carbocation to the product. But I don't think that's accurate. This other intermediate, again, has been determined experimentally to exist, and I think that also makes sense. In order to go straight from the carbocation to the product, what you'd need to happen would be that the water molecule would have to attack the carbocation and get deprotonated by another water molecule at the exact same time. That doesn't make sense. You're not going to have three molecules lining up just exactly correctly like that. That would be a vanishingly rare occurrence. It's rare enough for two molecules to collide in the right orientation with the right amount of energy in order to get a reaction. Termolecular reactions do exist, but they're extremely rare and generally only occur because of other extraordinary circumstances, which we certainly do not have here. So I think this makes the most sense. I think we need to show this as a three-step process. I guess this over here would be our third transition state. So 3 steps, 3 transition states. And I think we'll find the energy diagram to look something like this in general. Now, at this point on the energy diagram, again, as we said over here, the SN1 reaction is technically complete. It's over at that point. We've done the nucleophilic substitution. That's over at this point. We still have one more step to get a neutral product out. And I think you'll find, again, I don't know if I can say always, but I think you'll find that's pretty generally the case. Very, very common with SN1 reactions. So I am going to show you another example of an SN1 reaction. We'll go over that mechanism too. But I want to make sure that we're comfortable at this point. Any questions? Yes. I call them termolecular reactions. You might expect what, sorry? You might expect that to be the rate of step. No, I still wouldn't. Because both of those are very kinetically fast processes. The question is if somehow we could rig it so that you got that termolecular reaction, would that then be the rate determining step? No, I don't think so. I think breaking that bond is going to be the slowest thing of all. But yeah, you're not going to get, not in a situation like this, just, you know, with ordinary stirring of ordinary things in an ordinary flask, no, you're not going to get, not any significant amount, you know, one molecule in one time in 10 million might happen like that, but not enough to use that as a mechanism. Good, other questions then? Well, I'm going to show another example of an SN1 reaction, and at the same time cover the idea, or let's say the idea of chirality and stereochemistry in an SN1 reaction. Recall that in an SN2 reaction, we said that they always go with 100% inversion of configuration, provided, of course, that the substrate is chiral. at the reacting carbon. This is not the case for an SN1 reaction. And in order to show what I mean, let's make a chiral tertiary substrate. It's not hard to come up with something. Oh, I'm sick of bromide. Let's use tosylate. I really don't want people memorizing that it's always Br there. Not necessarily. Any good leaving group will do. So let's say we started with this compound enantiomerically pure. And I'm as positive as I know how to be that that's in the R configuration. And again, remember, tosylate is a really good leaving group, better even than iodide. So we talked about that in class, how to make it and what OTS stands for. Let's say that we heated this in, oh, I don't know, ethanol. What would we expect to happen? Well, again, the first step is going to be loss of the leaving group. So we're going to get our carbocation, but what do we know about the shape of carbocations? Remember, carbocation carbons are sp2 hybridized, so they're planar. So even though we started with an enantiomerically pure starting material, we just lost that. Right? This carbocation intermediate is achiral. So yes, some of you will be wondering, what if you drew that methyl group with a dotted bond? Would that lose points? Yes, yes, because that indicates to me that you're not aware that carbocations are planar. And that's significant here because it means that even if we start with an enantiomerically pure starting material, it'd be kind of a waste to do so in certain ways because after the first step of the reaction, that's wiped out. We've lost all trace of chirality. And for reasons that I think you'll see in a moment, I'm going to copy that intermediate over here because we now have two possibilities in terms of what can happen. Our ethanol can attack from the front or from above the molecule. And you can write from the front or from above if you want to clarify that, if you want to make that clear. Wait a minute. There we go. Is the carbon with stereochemistry connected? Did I do it wrong? Let's see. Did I lose a carbon? 3, 4, 5, 6. 3, 4, 5, 6. I think so. Yeah, there's 2 CH2s here and another one over here. So it should be, it's basically a 6-carbon chain with all the business happening on the 3rd carbon. Am I losing it? I think that's right. Since it's Friday, 1, 2, 3, 1, 2, 3. Okay, yes, I think we're in good shape. And anyway, if the ethanol, I thought chiral would have different, there's a propyl group, an ethyl group, a tosylate, and a methyl group. Those are all 4 different. There's 2 CH2s here and only 1 over here. So that carbon is chiral. Note, always pays to double check because God knows I make mistakes, but not this time. So if our ethanol attacks from above, what does that mean in terms of what we have to put? Well, it means that the bond to that oxygen is going to come in from above now. And this is one of the intermediates we'll get. 1, 2, 3. And so now we'll use again an ethanol molecule as our base, not ETO minus, we're not given that. I don't see any NaOET or anything like that. So we're going to use that. And also this means you don't just automatically put H2O here, right? You got to use what it is that you're given. And in this case, our solvent and our nucleophile are both ethanol. And so we'll pull that proton off, and that will lead to this alcohol. Which, unless I've lost it entirely, is still in the R configuration. But that's not the only possibility. We could also show the ethanol coming from behind. And again, if you want to make sure to clarify that, you can say from behind or from below. So you can put something like that to clarify that if you wish. And that will now make the attachment to oxygen on the dotted bond. And now the methyl group will be on the wedge bond. And so again, we just have, whoops, how about a plus charge? We just need one more step in order to pull off that proton. Again, we'll use the solvent that we're given, and we'll pull that proton off. It's not the best arrow I've ever drawn, but I'm showing that the electrons in that OH bond are going onto the oxygen, and now we'll get a product with the opposite stereochemistry. And so that one should now have the S configuration there. So what that means is we will get both, and you will know which you need to show based on how the question is phrased. If it says to show the mechanism for both, you'll show both mechanisms. If it says just to show how you get one compound, then you'll show just that one. But again, I don't want you guys to focus on that. Remember, if you get points in an exam taken off, even though your answer is right, then it's a grading mistake. You bring it up and you get it back, you know. But the way the question is laid out should make it clear. On OWL also, you know, sometimes they want you to show both. Sometimes they want you to show this just one. Other times they'll say, don't even worry about stereochemistry. So you just need to read the directions of the question in question, so to speak. But we do expect from this that we would get both enantiomers. So even though we started with a chiral starting material and it was enantiomerically pure, in the end, we will get a mixture of R and S. And again, you'll know which to put based on what the question says to do. But be that as it may, you would think that you would get a 50-50 mixture. In other words, a racemic mixture. Because it's not, at least at first, apparent that it is easier for the nucleophile to come from either side than the other. At least it looks that way at first. Theory would predict a racemic mixture. In actual practice, reactions like this are known to go with a slight favoring of the inverted product. And the reason is that when the leaving group leaves, it doesn't immediately diffuse away. It takes a little time to do that. So you have this anion sitting, in this case, since it's in a wedge bond, above the molecule. So there's a not insignificant length of time when that face of the molecule is blocked. And so the nucleophile will therefore have a slight preference coming in from the opposite direction of where the leaving group is. But in the end, you will get both. So I don't know that you would get 50-50. Just have to wait a minute. Oh, right, okay. In the end, I don't think you'd get 50-50 here of these two. I think in the end, it might be, oh, I don't know, 40-60 or 55-45. Results like that are pretty common with an SN1 type reaction, even though theory predicts 50-50. It's kind of a subtle point, but I feel that my job is, at least in part, to tell you the truth. And that's the truth about the SN1 reaction, that you will get a mixture of both products. And even though theory would predict 50-50, in practice, it isn't usually quite 50-50. In practice, it favors the inverted product, again, because the leaving group anion blocks the face of the molecule that it starts on for a not insignificant length of time. It's a subtle point, but I think it bears mention. Good, and I think that's all I need to say. Ooh, what I do over here? Goodness. I think that's all I need to say about that. Yes? What do you call protonated ethanol? Protonated ethanol is perfectly good, or the conjugate acid of ethanol. And it doesn't do anything. It just stays in solution, like the H3O plus ions did. Nope. Nope. Yes? I'm sorry? Oh, you can't, how can you calculate it? You can't calculate it. It depends on the reaction. There's no way to know it ahead of time. But I think in general, you would expect it to be something near 50-50, maybe slightly favoring the inverted product. Good, other questions? Well, I've got 3 minutes. Hopefully that's enough. We can actually go through, I think, the remaining characteristics of the reaction pretty quickly. And in the worst case, I can do like I've been doing the last few lectures and splice on the end of Section 504's lecture. For some reason, we always, I think you guys just ask more questions than they do. And neither way is better than the other, but if I need to do that, that's what I'll do in this case. How do you know the volume of solvent to use? I don't know, I would just use a very large excess. I would say it's based on, how much of your solvent. I mean, the best answer I can give you is I don't think I know. I don't think I've ever done an SN1 reaction in real life. But I would use, I mean, if I had to take a guess, I don't know. I'd maybe make it like 1% or 2% of the substrate compared to the solvent. I think that would be fine. I wouldn't want it to be too much more concentrated than that for sure. But that'd be my guess. Good. Again, just based on past experience with other reactions. Good, so what are some other characteristics of the reaction that are important to go over? Well, one thing also to be aware is since there is a carbocation intermediate, regardless of the fine details of the starting material, remember what that means. What do we always need to watch out for whenever there's a carbocation intermediate? Carbocation rearrangements. So especially if the starting material is secondary, you need to watch out, you need to look ahead at what you're given for the product and be ready for the possibility of carbocation rearrangements, which you can generally tell when you look at the structure of the product you're given, something's moved. So that's important. We need to be ready for that. I think we've already said that, tertiary substrates react the fastest. So that order of reactivity is going to be very much the opposite of for SN2 reactions. Tertiary substrates react the fastest in an SN1 reaction, then secondary, then primary, then methyl. We've already talked about leaving group ability. I've given you some pointers on how you can know whether a leaving group is good, bad, or indifferent. That's an area where SN1 and SN2 reactions are the same, right? For both of them, the better the leaving group, the faster the reaction. And again, we went over a typical order of reactivity for leaving groups, but it would make sense that's going to be the same for them both. What about the nucleophile? Well, that's almost a trick question. Since the nucleophile doesn't enter into the rate law and isn't involved in the rate determining step, the nature of the nucleophile has no effect on an SN1 reaction because it's not involved in the rate determining step. So that kind of makes sense, I think, when you think it through. What about the solvent? Well, the solvent situation is now the exact opposite as for SN2 reactions. For SN2 reactions, we said the best solvent of choice is a polar aprotic solvent. But polar aprotic solvents are only good at solvating anions if they're really little, if they're almost point charges, like Na+ or something like that. They're just not, they don't have enough of a polar area on the molecule in order to stabilize larger charged species, like carbocations. So you're not going to get a carbocation in a polar aprotic solvent. So you certainly do not, for a reaction like this, want to use acetone or DMSO or one of these things. Protic solvents are much better at stabilizing things like carbocations, as well as large anions like, I don't know, tosylate. Protic solvents are much better at solvating things like that because they do so by hydrogen bonding. So that's why protic solvents are the best choice for any of these unimolecular reactions. SN1, and as we'll find out on Monday, also E1 reactions. So that, I think, is basically it and puts us in good stead to start with elimination reactions and bring it all home on Monday. But I am out of time. So have a good weekend, and I will see you all on Monday.